Okay, so now we are going to use the NMOS inverter with enhancement load. So you can see this is an enhancement type NMOS. So this is enhancement type NMOS. So therefore, because it is replacing the load resistance, we are calling it enhancement type load. So in this problem, we have quite a huge list of parameters that we need to track of, just like VT and D. So the D represents the driver. So this main transistor, which should be responsible for turning on and turning off the output voltage. This is called the driver, and as previously mentioned, this top half is actually referred to as the load circuit. Okay, so we are given the input threshold voltage for driver and the load equals to 1 volt, and the conduction parameter for driver equals to 50 microampere. So we need to be careful about the microampere part, and the load circuit or the load MOSFET has 10 microampere conduction parameter, and we don't have to consider about this lambda and lambda NL and lambda ND. They are actually related to the channel, some parameters that is involved in non-linearity in the performance of the transistor. However, we are not going to use these parameters. Just focus on these other things, and we are given that the input voltage could be 5 volt and 1.5 volt, and we need to figure out mainly the output voltage, and we could also calculate the drain current if we actually solve for the output voltage. So let's consider the first case, that is now V1 is equals to 1.5 volt. Okay, so here is a very important thing about this configuration, that the gate voltage is connected to the drain terminal for this load circuit. That means that the drain VDS is equals to VGS, because drain and gate are now at same voltage. That means that VGS minus VTN equals to VDS, because now for this we should put a L here to actually specify this is, we are talking about the load circuit. So VGSL, VTNL and VDSL minus VTNL, because VTNL are, and this is 1 volt, therefore it must be less than VDSL. So we can safely assume that the ML will operate in saturation mode, no matter what the input voltage is. Okay, so let's use our intuition about the inverter. Because this input voltage is high, you can safely assume that the driver circuit or the driver MOSFET is operating in triode region. So and another thing we should note here, the drain current through this load circuit and the drain current through this driver circuit should be equal, because there is no other extra circuitry is connected to this circuit. Therefore there can be no possibility of changing the current flowing from load to the driver. So we have ITL equals to ITGL T, and if we use the formulas for IDL and IDD, we are here it is operating in saturation and this is operating in triode. We have the formula like this: KNL VGSL minus VTNL square equals to KND, because this is now driver, 2 times VGSD minus VTND times PDSD minus VDSD square. Okay, so this should be the equation and we need to plug it in now. KNL, so KN is given that 10 micro, so 10 micro ampere per volt square, that is 10 divided by 1,000 will give us the milli, that is 0.01 milliampere per volt square, 0.01. VGS, the gate voltage, gate is now connected to the 5 volt here, or drain, so we can write 5, but we don't know the source here because the source terminal is connected to the output voltage, so we need to careful about the source terminal here. So now the source is V0. Okay, so now VTML, both of these threshold voltages are same, so this is that. Now ALD should be 50 microampere. This is, therefore this is 0.05 milliampere per volt square, 2 times gate source. Now the gate voltage here is 1 point, oh sorry, this we are considering, this should be 5. We are actually using this one. I just mistakenly wrote 5 volt here. So 5 minus, now for the driver circuit, source is connected to the ground, 0 minus, now the threshold voltage 1, VSD, this is the output or the drain voltage for our driver circuit, that should be V0, and source terminal is connected to the ground. We should careful about the source terminal, and again V0 square. This will lead to 6 V0 square minus 48 V0 plus 16 equals to 0, and finally we have V0 equals to 7.65 and 0.34, and it is obvious the 7.65 is not the answer because the maximum voltage here is 5 volt, and if we pick the correct one, this should be incorrect, this is correct, and from there we can plug in this output voltage to, let's say, this formula, and we will get the load current as well as the drain current, and the formula, the result would be 0.133 milliampere. Okay, so when we are plugging in this formula, we should be careful about the formula here, 0.01. Okay, so now let's proceed. In this case, we are going to consider the input voltage equals to 1.5 volt. Just like before, the load ML should be in saturation. No matter what the input voltage is, ML is always in saturation. Even if the input voltage is 0 volt, the uh, driver circuit would cut off, but the load circuit would still in saturation. However, the drain current would zero. That is a bizarre situation, but it will occur in real life. Okay. And we have, for this condition, we will assume that the MD is in, let's say, saturation. This is our assumption. Okay, so MD is in saturation is our assumption. Let's check it out. Again, our drain current are equal. So it will give us KD1, KDL, sorry, VGSL minus VTNL square equals to KND VST minus VTND square. Okay, so now let's plug in the results. We have 0.01 here. Now the gate voltage is again connected to the 5 volt for load circuit. 5 minus the source is now the output voltage, phase 0, minus 1 square, now 0.05. This will give 1.5. Now the input voltage is 1.5 minus the threshold voltage, that is 1 square. So from here we can actually easily solve for V0, and the V0 would be 2.88 volt, because we take the square root in both sides and keep the positive part of the square root and solve for this. It will give us VDS, that is 2.55, which is greater than, you can easily see this is greater than VI minus VTND. So it is clearly satisfies our assumption. So the output voltage is 2.88 volt, and we can, from here we can calculate the drain current. So the drain current should be, let's plug it in here, 0.05, 1.5 minus 1 whole square. It is about 12.5 microampere. Okay, so this answer is in milliampere, and we multiply it with 1000 to get the result in microampere. Okay, so this is all for enhancement mode type load. Now let's check out the depletion type load. So as you can see here, there is a colored section at the channel region. That would mean that this transistor is a depletion type transistor. Therefore, the threshold voltage for this load MOSFET would be negative. And here we have the negative threshold voltage. And this colored region actually means that whenever the gate voltage is zero, the channel is turned on, or the presence of the channel. Okay, so therefore we need to apply negative threshold voltage to actually turn off the channel, or put this MOSFET into cutoff region. Okay. So another thing to note here, we are given K prime N. So this K prime N is actually called the process parameter. Okay, so the process parameter and the conduction parameter is related like this. The capital Kn is related with small k prime n times W by L. Okay, so this is conduction parameter and this is the process parameter. This is small k. Okay, so for this problem, we need to actually use this formula in order to get the correct result, and we are asked to neglect the body effect. We will, in CSE460 course, we are going to give a deep dive about the body effect in NMOS or PMOS type transistors. Okay, so for this problem, we are given two inputs, and both at input A and input B, and both are at 2.5 voltage. So therefore, this is a NOR gate actually. So therefore, the both inputs are high voltage. Therefore, the output should be in low voltage. Okay. So what about the operational mode? So let's say about the load circuit, the load MOSFET. Okay, so here the gate terminal is shorted to the source terminal. So we have VGS, that is equals to 0. This is clearly equals to 0 volt. So therefore VGS is always greater than VTNL. That means that ML transistor is always on. ML is always on. But which mode now it is operating? ML could be operate in saturation and triad mode depending on the output voltage. So we cannot actually say for sure what is the operational mode. But for these input voltages, we can make a very good educative guess. So what should be our guess here? So because this is a NOR circuit and the input voltages are high, so the output voltage would be is small. Okay, so because the output voltage is small, now the VDS should be drain voltage is 2.5 and the output voltage is something smaller value, then the VDS should be much high voltage. Okay, so this should be, let's say, around 2 or something 1.8 volt maybe, because now the VDS is high. We can safely say that VDS is greater than VGS minus VTNL. This may not be true, because it could happen that both of these transistors in the driver circuit would turned off. But for this condition, we can almost say that the VGS is 0 and the VTN is around minus 0.6, that is 0.6. Okay, so we can actually like this, that the V0 is small, therefore VDS would be around 2.2 or 1.8, and that would be much higher than the 0.6. So we can actually almost certainly can say that ML is operating in saturation. But if the input voltages at these two terminal A and B would be different from 2.5, let's say both are in 1.5 or 1 volt, then we can actually cannot say for certain what is the operating mode for the load transistor here. Okay, so now we proceed to our main calculation. Because these two section or these two transistors, two MOSFETs are actually identical, because they both have the identical input, and the other parameters, the load parameters, are actually equal. So we can actually just multiply the current here to get multiply this current into 2 to actually calculate the ideal or equate this formula. Okay, so we have IDL equals to IDA plus IDB, and ID and IDB is equal because of the symmetry, but you must be careful that both the input could be different or the other internal parameter could be different. Then you need to actually calculate the drain current differently. We just here we are just using the symmetry IDM. Now this should be capital K NL PGSL minus VTNL squared KNT 2 times PGSD minus VTNT times VTSD into VTSD square times 2. The 2 is here because we just discussed just now. Okay. So now we can write it like this: Kn prime W by L for load circuit, and this is Kn prime W by L for driver circuit. We just cross out this KNL from both sides of the equation, and then plug in the values. So W by L for load circuit is given is 1, and W by L for driver is 4. So this is 4, this is 1, and VGSL. So this V, G, and S, because these two terminals are sorted, so we have calculated the VGSL previously. This is 0. VTNL, this is minus 0.6 whole square. Okay, and now VGS, the gate voltages, both gate voltages are 2.5. So 2.5 minus the threshold voltage. The threshold voltage for drain current is actually 0.4, and VDS, this is V0. Again, this one is V0 square. So if we simplify this formula, we will get 4V0 square minus 16.8 V0 plus 0.36 equals to 0, and this will lead us V0 equals to 4.178 volt and 0.02153 volt, and this shouldn't be the answer because this is higher than 2.5 volt, and this should be the correct value. And we can actually check whether this value would satisfy the triode condition for MTA and MDB and saturation condition for ML, but you can do it for yourself. And from here we can actually calculate the drain current using the formula. Let's say we can use the ideals formula to calculate the drain current here. Ideal equals to K prime N, that is 100 microampere per volt square. That should be 0.1 milliampere per volt square. W by L is 1, and we have minus 0 minus 0.6. This is 0.6 squared, and it should be 0.36, 0.036 milliampere. And IDB should be half of IDL because they are symmetric, and this is 0.018 milliampere. Okay. So that concludes the discussion about mainly the NMOS families, and the similar goes for the PMOS families. In our next lecture, lecture 12, we are going to discuss about the typical CMOS families. And for this discussion, we have used these two chapters from Niemann's book. You can find the Niemann's book in course handout section of our backspace. So that's all from us today. Thank you for listening.